Look around you. Everything you see, from the screen you're watching this on, to the stars twinkling in the night sky, all of it makes up a surprisingly tiny fraction of what's actually out there. All the matter we can observe, all the planets, stars, galaxies, and gas clouds, accounts for only 5% of the total universe. So, what about the other 95%? This immense invisible majority is composed of two mysterious components: dark matter and dark energy. They are the unseen architects of the cosmos, locked in an epic silent battle that will determine the ultimate fate of reality itself. To understand this cosmic struggle, let's first look at the force that tries to hold everything together: dark matter. Think of it as the universe's invisible scaffolding. Can't see it, we can't touch it, and it doesn't interact with light or any other form of electromagnetic radiation. Its existence is inferred purely through its gravitational effects on the things we can see. The story of dark matter begins in the 1930s with an astronomer named Fritz Zwicky. While observing the Coma cluster of galaxies, he noticed something strange. The galaxies at the outer edges were moving far too quickly. Based on the visible matter within the cluster, the gravity should not have been strong enough to keep these speeding galaxies from flying off into deep space. It was as if an unseen mass was providing the extra gravitational pull needed to hold the cluster together. Zwicky called this missing mass Dunkle Materie, or dark matter. For decades, his idea was largely dismissed, but more evidence began to pile up. In the 1970s, astronomer Vera Rubin was studying the rotation of individual galaxies. She expected to see stars at the outer edges of a galaxy moving slower than the stars closer to the center. Just like the outer planets in our solar system orbit the sun more slowly than the inner ones. But that's not what she found. Instead, the stars at the galactic fringes were moving just as fast as those near the core. This defied the known laws of physics, unless there was a massive, invisible halo of matter surrounding the entire galaxy, providing the extra gravity to keep those outer stars in their orbits. This was the smoking gun. The rotational curves of galaxies provided compelling evidence that this invisible substance was real and abundant. Today, we estimate that dark matter makes up about 27% of the universe. It clumps together, forming vast, invisible structures that act as gravitational wells. It was these wells that allowed the first particles of ordinary matter in the early universe to gather, eventually forming the first stars and galaxies. Without dark matter, the structures we see today, including our own Milky Way, would likely have never formed. It's the silent force of construction, the cosmic glue that pulls matter together, building the grand tapestries of galaxies and galaxy clusters we observe across the cosmos. But while dark matter pulls, another even more mysterious force pushes. This is dark energy, the dominant component of our universe. If dark matter is the force of cosmic construction, dark energy is the force of cosmic expansion, and it's winning the battle. Dark energy makes up a staggering 68% of the universe, more than dark matter and ordinary matter combined. Its discovery was a complete shock to the scientific community. For most of the 20th century, astronomers debated the fate of the universe. Would gravity, aided by the unseen mass of dark matter, eventually halt the expansion that began with the Big Bang and cause everything to collapse back in on itself in a big crunch? Or would the expansion continue forever, with galaxies slowly drifting apart? Two independent teams of astronomers set out to answer this question in the late 1990s. They used distant supernova, a type of exploding star with a known brightness, as standard candles to measure the expansion rate of the universe throughout its history. They expected to find that the expansion was slowing down due to the pull of gravity. What they found was the exact opposite. The expansion of the universe is not slowing down, it's accelerating. Something is actively pushing space-time itself apart, causing galaxies to fly away from each other at ever-increasing speeds. This mysterious anti-gravitational force was named dark energy. Like dark matter, which clumps together, dark energy seems to be a property of space itself. As space expands, more space is created, and with it, more dark energy. This creates a runaway effect. The more space expands, the more dark energy there is, which in turn causes space to expand even faster. It's a relentless, accelerating force that is stretching the very fabric of the cosmos. So, we have a cosmic tug-of-war on a grand scale. On one side, we have dark matter. It's gravity trying to pull everything together to build and maintain structures. On the other, we have dark energy, an intrinsic property of space that pushes everything apart with increasing ferocity. In the early universe, the cosmos was much denser, so the gravitational influence of dark matter was dominant. It was the master builder, allowing galaxies to form and cluster together. But as the universe expanded, the density of dark matter and ordinary matter decreased. The influence of dark energy, however, remained constant or even grew, as it is a property of space itself. About 5 billion years ago, a cosmic tipping point was reached. The repulsive force of dark energy became stronger than the attractive force of gravity on the largest scales. The era of accelerated expansion began, and the fate of our universe was sealed. So what does this cosmic battle mean for the future? Dark energy continues to dominate. The universe is heading towards a chilling finale, known as the Big Freeze or heat death. The accelerating expansion will carry distant galaxies away from us so fast that their light will eventually be unable to reach us. Future observers in the Milky Way will look out into a dark, empty void with no evidence of other galaxies. The cosmic horizon will shrink, and our island universe will become truly isolated. Over unimaginable timescales, the stars within our own galaxy will burn out. The universe will grow darker, colder, and emptier, eventually reaching a state of maximum entropy where nothing happens. It will be a vast, silent, and eternally dark cosmos. The invisible 95% of our universe dictates its past, present, and future. Dark matter was the architect of the cosmic web, the gravitational sculptor that allowed us to exist. But dark energy is the ultimate victor, the force that is now tearing that creation apart, leading us toward a cold and lonely end. We live in a special, fleeting moment in cosmic history, a time when we can still observe the grand tapestry of galaxies before they are pushed beyond our view forever. Understanding these two great cosmic unknowns is one of the biggest challenges in modern physics. It's a journey into the heart of what makes up reality, a quest to understand the fundamental forces that govern everything. The universe is far stranger and more mysterious than we could have ever imagined. Thanks for joining us on this journey through the invisible cosmos. If you enjoyed exploring the mysteries of space with us, be sure to subscribe to Space Repo for more deep dives into the universe.